Civilization doesn't end where the sunlight fades, it just has to start making its own. Between the stars and the ice. We recently looked at how to turn asteroids into enormous and prosperous settlements in our Asteroid City-State episode, but I felt there was more to discuss to take that to look at the Kuiper Belt and beyond. The belt has taught us how to mine, refine, and build in places where sun is no brighter than a distant floodlight, but the frontier does not end there. The solar system stretches on for trillions of kilometers, a realm of faint light and frozen oceans, and humanity has never been good at stopping. Beyond Mars and Jupiter, the sunlight thins, the planets grow sparse, and the sky fills with cold wanderers, the comets and ice balls of the Kuiper Belt, the halfway house between the inner worlds and interstellar space. Out here, we don't just build cities, we build sanctuaries against the dark. The questions are simple enough to ask, but vast enough to fill a civilization. First, how do we live, work, and communicate when even the sunlight itself fades away? Second, why would we want to? The same skills that turned rock into refuge now must evolve to turn isolation into permanence. In the belt, energy and metal were plentiful, and neighbors were only minutes or at most an hour away by radio. So that fission might be better while uranium supplies last, and fusion is nice if you got it, but you can still use the sun for direct power, and signals are simple. Beyond Neptune, warmth and even bandwidth are luxuries, and yet that challenges the very definition of frontier. It's where every generation of explorers has looked and said, let's see how far we can go. From city-states to deep stations. The journey from the asteroid belt to the deep frontier begins where the sun is just a bright star in the Kuiper Belt, 30 to 100 astronomical units from home, and many times more massive than the asteroid belt. Beyond that lies the Oort cloud, a shell of icy bodies extending perhaps halfway to the nearest star, with inner regions around 1,000 AU and the outer boundary stretching to 100,000. It's a realm where space isn't empty, just quiet. Millions of small frozen worlds drift there, untouched, waiting to become the raw material of a new civilization. Beyond this range is true interstellar space, beholden to no star but potentially still useful for connecting star systems. The habitats we will build here fall into three broad families. The first are converted bodies, asteroids, comets, and icy dwarfs, hollowed out to provide matter to build with and fuel to run on, and space-to-place habitats shielded from the outside. Their rocky cores provide shielding. Their frozen mantles hold the volatiles needed for air, water, and fuel. A single 10-kilometer object contains more usable mass than several entire O'Neill-cylinder space habitats would need, and each would be larger than that in volume. The second type are free-floating stations, wholly artificial habitats, like those O'Neill cylinders of the more modest Stanford Taurus, which might support just a few thousand people in comfort, built from refined materials or recycled metals shipped outward from the belt. These are the ultimate expression of orbital engineering, modular, optimized for power efficiency, radiation protection, and long-term autonomy. They can cluster together like city constellations, each a world unto itself, yet linked by light. And then there would be our rarest class, those built on actual rogue planets in the void with their own gravity. The sheer resources available here make them ultra-valuable prizes, and more than a stepping stone between stars or a minor isolated enclave for those wanting to be left alone. They are in many ways a mini solar system, and might range from worlds a bit smaller than even Pluto to full-scale gas giants or even brown dwarfs. Each new habitat is a promise that distance no longer defines civilization. What begins as city-states of the belt now becomes the stations of the deep, a civilization scattered across light days of emptiness, yet bound together by technology, ingenuity, and the stubborn human refusal to let the dark remain empty. But for the light of civilization to shine, it needs a power source, and with the sun so distant, the viability and scale of such habitats depends a lot on the power generation technology available. Fission, the fire that never fails. It's difficult to speak with confidence about energy technologies that don't yet exist. We may, after all, someday learn how to draw power directly from the vacuum, or the fabric of space-time itself, and that would change the game completely. But there are a lot of ifs and buts in such scenarios, even for something as near and yet elusive as fusion, where skeptics have every right to ask whether it will ever become practical, and whether deep space habitats are doomed without it. So let's begin by examining our options if fission is all we've got. Fission may not be glamorous, but it's the power source that may need to get humanity everywhere. Unlike fusion, which we'll get to in a moment, It's a technology we've already gotten fairly skilled with, though by no means mastered. It has two main weaknesses relative to fusion. First, it is a bit less energy dense. Both can extract millions of times more energy from a given amount of fuel than chemical propellants, like gasoline or rocket fuel, but fusion outperforms fission by roughly an order of magnitude. The second, and arguably greater problem, is that fission fuels are vastly less common than fusion fuels. Hydrogen, deuterium, and helium, our default fusion fuels, make up most of the ordinary matter in the universe, while uranium and thorium are rare trace elements, measured in parts per million, and plutonium scarcely exists outside our reactors. When sunlight fades and fusion remains a luxury, fission reactors keep the lights on. They are steady, compact, and forgiving of distance. Even a ton of uranium or thorium can yield more usable energy than a mountain of chemical fuel, and with modern breeder cycles, nearly every atom can be tapped. A deep space habitat doesn't need to refuel often, perhaps once a century. Most run sealed reactors built to last longer than their founders' lifetimes, recycling waste heat to warm hydroponics bays and melt ice for water. Their glow becomes civilization's campfire in the dark, a reminder that the oldest nuclear fire still burns long after the sun itself has dwindled to a faint spark. We might even imagine a starship with a forward shield made of uranium, 100 meters wide and 1 meter thick, serving as both protection and fuel reserve. That slab would mass around 150,000 tons and contain roughly 12 trillion gigajoules of potential energy, enough to run a gigawatt reactor for about 400,000 years. That could comfortably light a Stanford tourist habitat, providing warmth, food, and daylight for several thousand people for as long as humanity has existed, all without resupply. Thus, fission is more than a stopgap. It is the foundation on which every deeper venture can be built if necessary. It may be used even if you get fusion working too, as it's likely that fusion reactors will always be large affairs, whereas small fission and radioactive isotope thermal generators may be more practical in many cases. But scarcity will shape that role. Analysis of meteorites, the fragments of asteroids and comets we can actually study, show uranium and thorium concentrations around 5 to 20 parts per billion, compared to roughly 1,000 parts per billion for uranium in Earth's crust. In other words, these atonine elements are tens to hundreds of times scarcer in primitive small bodies than are enriched continental rocks. It is not that they do not exist, just they're thinly spread, dissolved into dust and stone rather than garnered into easily accessible ore. Take a typical Oort cloud object 10 miles across, about 16 kilometers in diameter, with an average density of a ton per cubic meter, a mix of dust and ice. That gives a total mass of about 2 trillion tons. At those trace abundances, it might hold 5 to 20,000 tons of uranium and thorium combined. Even at that level, it's still enough, in principle, to power a gigawatt-class reactor for a few millennia, depending on how efficiently it's mined and burned. Scale that up to a 100-mile wide ice ball and you have 1,000 times more material, enough to run such a reactor for many millions of years. From a practical standpoint, your Stanford tourist habitat needs to come up with a new ton of uranium every 3 months to 3 years, depending on your efficiency of use and real power demands. You get that by trade or local mining, and for a modern context, a ton of yellow cake uranium runs a couple $100,000. It's not cheap, especially if you're shipping to the outer solar system, but it's likely to be less than 1% of your total economy, and thus no big bottleneck while supplies last, and interstellar shipping at maybe 0.1 to 1% of light speed would be economically viable. So the fuel is there, just spread thinly. A civilization with nuclear thermal drives, robotic miners, and breeder technology could sift it from countless worlds, concentrating the way ancient prospectors panned for gold. And once we have breeder reactors converting fertile thorium into fissile uranium, or reprocessing spent fuel into new stock, that trickle becomes a steady current. Fusion. Bottled stars for cold worlds. Where fission splits, fusion unites, pressing light elements together to release the same power that fuels the stars. It is harder to tame but infinitely cleaner, and for worlds beyond the sun, it promises a civilization that no longer needs to worry about being short-lived compared to those living near stars. Early settlers may rely on deuterium-tritium reactions harvested from cometary ices or ammonia-rich bodies. Tritium might be created by fission reactions too, but mature outposts will chase purer fuels, deuterium, helium-3, proton, boron, or maybe even pure hydrogen fusion. That's a much heavier lift to make economically viable, but there is a lot more of it as a fuel too. Each reactor becomes a miniature star, its magnetic coils and containment rings holding a sphere of plasma hotter than the heart of the sun. That's right, the core of the Sun is not actually hot enough for our purposes for having commercial fusion. Fusion's virtue is independence. A few tons of deuterium can power a city of 1 million for decades, and every ice-covered rock in the Kuiper Belt is a potential fuel depot stretching for eons. Its waste heat can drive greenhouses, smelters, and even propulsion for station-moving thrusters. With fusion, a habitat need not ration its dreams. It can grow, terraform, or voyage. Somewhat ironically, fusion reactors decrease our need for deep space habitats, even as they make them much easier, as a fusion-powered starship no longer needs stations between the stars to make its journey viable. But as we'll see, both today and our upcoming Interstellar Relays episode, there's still plenty more reasons, and the remainder all work better if you have power. Fusion is also not our ultimate power source. That would fall to options like antimatter, matter-to-energy converters, vacuum energy perhaps, or micro black holes, which we'll return to in a bit. But if we can get it working, it means we're not bound to the solar system anymore, and we can power huge local pushing beams such as those we'll discuss shortly. The beamed power web. The Sun gives off a couple billion times more energy than Earth uses to keep itself warm and lit, so converting some of that extra power into microwaves to beam out to the asteroid belt, outer planets, or even the Kuiper Belt is very much an option. Our main issue is that even beams and lasers spread out over distance. We'll deep dive that in our Interstellar Relays episode I mentioned earlier, and which forms a loose trilogy with this episode and Asteroid City-States. But from a practical standpoint, when talking about beaming billions of watts of power to someplace, you can only focus it out to a handful of AU with microwaves and a few thousand AU with lasers in the visible infrared range. And even then, this requires immense, kilometer-scale apertures, and receiving hardware even wider, if far simpler. You can increase the scale of that hardware for even more range, but now you begin needing hardware bigger than the stations and habitats they would support. And we mean more in terms of mass here. Size itself is not too big a deal in empty space. You could have a parabolic mirror behind a space habitat that was 100 times wider than it was, and thus could let it enjoy noontime sunlight 100 AU away from the Sun. But that's because it's a tinfoil thin mirror, still missing only a small fraction of what the habitat itself does. And we can widen that range by aiming a laser that way instead of regular sunlight, but there are limits, and your best case scenario for capturing power and resending it to a station further along the line is perhaps 50% efficiency. Probably less, but even then, if we assume a relay could pass 50% of the power it received down the chain, at 10,000 AU increments between relays, then a halfway point between Earth and Alpha Centauri is 15 increments out, and 15 halvings is just 1 in 32,768. That's a huge loss of power along the way, but I should note that even if you need a whole gigawatt at that center point station, or 32,768 gigawatts when left some beaming array hovering over the Sun's north pole, and if we needed 10 times that to power the other relays along the way too, that's still less than a trillionth of the Sun's power output. I think that interstellar civilization would not consider such a line all that unreasonable. But that's a far cry from wanting tons of stations out there, and it means only such relays are getting built out beyond maybe 1 or 2 relay junctions. There is going to be some practical maximum distance you can send power without a relay. If that turns out to be 4,000 AU, 100 times further out than Pluto ever gets, then that's when you stop seeing habitat that doesn't need to be out there. It also puts a deep crimp in trying to have intergalactic relays, but deep space outposts for monitoring for enemy ships or running patrols or mega telescope arrays might well be out in deep space too. They become rare and run on fission where possible instead. Thus we see that even without fusion, existing technologies for fission and beam power let us keep the light on 1 trillion miles from home, or 13 trillion miles in the case of our center point station. It is also possible to create fissionable fuels out of lower mass objects by dumping energy into them, and at a certain point that might actually be economically viable, much as we sometimes talk about making artificial gasoline or methane by using solar energy to power that process even at a loss. Clarketech power supplies. Power is vital to this topic today, so it's worth dwelling on, but for my part, I think we will get fusion working eventually, and I don't think it's our top tier either. We never know what sufficiently advanced magical technology will pop up, but micro black holes, even those in the trillion-ton range, which might be way easier to make than a Kugelblitz megaton black hole, are probably allowed under known physics. The trick is in making them. See our Black Hole Tech and Kugelblitz black holes episodes for deep dives of them, but they are interesting in that the scale is opposite to size. The smaller a black hole is, the more power it produces. They are also likely to be exponentially harder to produce and refuel. A black hole 30 trillion tons in mass is as wide as a hydrogen atom and only gives off about 1/3 of a watt, so I tend to feel it is refuelable. But it's also not terribly useful for generating power either by Hawking radiation or the Penrose process, which needs a bigger black hole. You may use this on larger bodies as a way of generating both gravity and power for a shell world on a rogue planet, as opposed to a spin gravity habitat. Alternatively, vacuum energy might be equivalent of filling water reservoirs from a large drainage basin. They may need truly immense volumes to work, see that episode for details, in which case deep space habitats might become the norm, since there's just so much more deep space than everything else, and those would actually be very awesome for intergalactic bridges. Outposts of Life. When we speak of colonizing the deep frontier, what we're really talking about is how to carry home with us into the dark. A habitat in the asteroid belt does not need to be ecologically self-sufficient. No place other than Earth likely ever would be. Arguably it isn't either in the long run, but there's degrees and timelines, and an asteroid base is close enough to receive seeds and stock from Earth regularly to shore up problems. The further out you go, the further you will be from Earth to other large habitats that can handle long-term isolation, and Oort Cloud Station might be 1,000 times further from Earth than a belt station. Hence, it must be a living world in miniature. While it can purchase information and genetics from neighbors or from Earth, this will be far harder. This is why I put a Stanford torus as an absolute minimum size for such habitats. They do not have a lot of living area, a bit under a square mile or 571 acres, or 230 hectares. You are also not likely to be supporting a population big enough to likely support a ton of biologists and geneticists, so your options are a bit limited unless your automation is so smart and so good that you can easily afford to build bigger stations anyway. Relay stations might get one or more spaceships stopping at them every year. Passing by is very different than stopping instantly. You don't really pull a spaceship over for a pit stop due to the rocket equation, but some stations sitting at 1000 AU in the void, still in the nearer range of the Oort cloud, might be lucky to get a dedicated cargo ship coming to it once a decade from the inner system. Every deep space habitat is, at heart, a machine for maintaining complexity, the same job Earth's biosphere has performed for billions of years. Inside a great torus or cylinder or sphere, a web of machines simulate sunlight, gravity, and weather, while bacteria, algae, and plants perform the hidden labor of turning waste into sustenance. But this is not a task they had to do on their own, and odds are good if you're living out there you may not want to be very reliant on the inner system. Much as in the asteroid belt or the Kuiper belt, trade between neighboring habitats can allow specialization, and in a biological context that means stations can dedicate some of their time and space to maintain specialized ecosystems or chunks of biology. When the station that only has 10 horses starts worrying about it in breeding, they can ask a neighbor for some frozen embryos of their horses in the next routine shipment, or put in an order from some station more focused on that. Or if that place is fairly far off, ask its neighbors who's interested and have the shipment sent to them to be divided among interested parties in later shipments when it arrives. Every non-microscopic organism in your habitat is going to need refreshing eventually, maybe them too, but in some cases a couple thousand years might be fine. Assume you have a dedicated specialist or more who simply has the job of collecting samples constantly and checking for degeneration, then putting in orders. There's a maximum timeline for frozen samples too. We don't know what the practical timeline is, but it's at least a few decades, maybe a lot longer. And speaking of freezers, you might have a lot more ships operating out in deep space that use cryo for passengers or even crew. I think you would see a lot of circuit traders. I would also bet big freezer banks of genetic refreshment material would be a big trading item, as it doesn't need to take a lot of space. As for trade inward, here we have a problem. The only material to offer is raw bulk material and mostly ices, and those would never be a super profitable item, whereas you are dependent on Earth and the inner system for science, entertainment, and new technologies. In time, as we colonize and our numbers grow, that ceases being a monopoly, as you can reach out to other neighboring systems. And a developed solar system probably doesn't operate a lot of effective monopolies either, and I'd be surprised if it was a single unified realm anyway. This is why, once established, you either need to be very self-sufficient or able to offer a service. Relay stations have one by definition, the highways between stars, and the telegraph posts. So would subsidized outposts or defensive monitoring stations. These could serve as lost leaders for the regions around them, anchor points of infrastructure in the Great Dark. A Kardashev Type 2 civilization might think nothing of maintaining a few million star fortresses arranged in a vast shell 50,000 AU out, just under a light year from its star. Each would be spaced roughly 100 AU apart, less than a light day of separation. That's about the width of the Kuiper belt, so even such titanic networks would hardly be crowded. If every outpost housed a Stanford Taurus or two, supporting perhaps a battalion to brigades worth of personnel and families buried beneath kilometers of armored rock, then even manning the entire grid might require no more than Earth's current population, perhaps several times that. But to accomplish a two civilization with billions of times our present numbers, that's a trivial investment, yet still the foundation for a vast secondary economy to grow around it. Indeed, because it is such a small investment considered to its value in protecting you from being wiped out by an enemy, I would be surprised if it wasn't at least an order of magnitude more robust. You could imagine small, self-reliant communities, kind of futuristic Amish, content with their isolation, building stations out there to farm, fabricate, and trade with nearby defense outposts. They might ship half their harvest to production in exchange for few resources they can't make locally, refined metals, specialized components, or update information from home. They get it all cheaply and regularly, riding the same supply routes already feeding the military and relay network. Same reasoning, someone wanting to set up telescopes or other science outposts out there no longer needs as much self-sufficiency, and it's a key idea that we discussed several years back in Crawlonizing the Oort Cloud, that even though they'd be tiny compared to the civilization nearer the Sun, which might number many quadrillions per solar system, they would still be quite numerous compared to us now. I also feel like such isolated outposts just beg for someone to write a story about them, so feel free to steal the idea for a book. In terms of power supply, fusion sure helps here, but even something as grand as this defense network I threw some numbers out for, manned by several billion people, is only needing a couple megatons of uranium and thorium a year to operate the whole thing. Earth's crust alone could supply that for 100 million years. Something to remember the next time someone suggests we can't run nuclear fission for long on Earth without running out, particularly as these folks are using almost all their power generation to provide artificial sunlight too. As you might guess, making these episodes involves a lot of time at a desk, and over the years I've gone through quite a few. If you spend long hours working, being able to change posture matters. Sitting is fine, standing is fine, but staying in one position for hours really is not. That's especially true if you've got kids or younger students trying to develop good study habits, where a standing or adjustable desk can be a great gift, especially if they like to move around or fidget. That's why I set up this Flexispot E7 standing desk, which was easy to assemble and let me get right to using it. The E7 has programmable height presets, so I can switch smoothly between sitting and standing with the press of a button, or different users. Unlike lighter desks that rely on thin aluminum frames, the E7 uses automotive-grade steel, and even its standing height is extremely solid. You can see it lifting with weight on it, including a couple of very enthusiastic helpers, without a wobble. It's rated for 355 pounds, which is more than enough for real-world use. Flexispot backs it with a 15-year warranty and a 30-day free return. If you're interested, visit Flexispot's website, check out their sales page, and use the code YTE730 for $30 off, so you can work more comfortably and productively while helping out this show. Just use the link in the episode description. Worlds of ice and thought. Many of these stations might be free-floating, indeed most would likely be constructed in the inner system, probably in the asteroid belt, then hauled outward even if they're destined to be embedded within an ice ball. For many, though, that ice ball becomes the perfect home. Every habitat leaks over time and needs new supplies of volatiles to replace what's lost. They also need raw materials for local manufacturing and limited export, and thick walls of ice and rock offer ideal radiation shielding, and even some protection against attack. You could easily fit a Stanford Taurus inside a mile-wide ice ball, carving out a crater or depression to seat it and using the excavated material to build an armored igloo shell around the structure. Many stations might still deploy enormous antennae or sensor arrays floating nearby, but those ice balls are valuable real estate. If not strictly necessary, then certainly desirable. They provide room to expand, insulation from radiation, and independence from outside support. So how many such worlds could there be? Probably 100 billion or more, perhaps even low trillions, in our own Oort cloud alone. We don't know for sure, and it would vary from star to star, but the deep frontier likely offers more potential homes than there have ever been humans to fill them, and as you fill them up, you might drag smaller icy bodies to you, or simply keep a smaller outpost there for automated mining, maybe overseen by a small crew you switched out annually. Loosely speaking, for objects of a given size, there's an inverse relationship to frequency, so objects a tenth the size of the ones you want to make homes are 10 times more common. They can also be ideal for nomad colonies, where some spaceship, like a colony ark, that decide not to try to make the whole journey, might latch onto one and be drained over a few years before moving to the next, and maybe they slowly circle around other permanent habitats trading people in goods and skills. Crawlonizing. As I mentioned, we'll soon have an episode on interstellar relays, and part of that will explore moving ships between star systems at a significant fraction of light speed. But as such networks prove impractical, or in the eras before they exist, deep space habitats and stations still have a vital role to play. Even if interstellar pushing beam stations do get built, they won't need to run the whole distance between stars. A beam can only stay locked on a ship for so long, and how much speed we can give it depends on how long we can hit it and how hard. From a practical standpoint, a beam that can push for 100 AU at 1 gravity acceleration would boost the ship to about 6% of light speed. Doubling that velocity to 12% requires 400 AU of beaming, and reaching 10 times that, 60% of light speed, would need roughly 10,000 AU of range. Beyond that, the return diminishes quickly, so relay stations, massive beamers spaced through deep space, make perfect sense. And it's not just about energy beams. The same infrastructure can send matter beams or accelerated cargo pods, hurling materials and supplies across the void. But of course you have to slow down at the far end too, which means mirrored infrastructure on the receiving side. Alternatively, you can take the slow path, a relay of outposts, not to beam ships across interstellar space, but to creep civilization outward, station by station, world by world, until, even moving at less than 1% of light speed, humanity eventually reaches another star. We call this Crawlonization. It's a quiet, patient advance, one that grows a civilization like lichen across rock, steady and unstoppable. If we expand this way, adding new layers of stations every few decades, inching outward even 1,000th of light speed, then within a few thousand years our reach extends to the nearest stars. In a few million, the entire neighborhood is connected, and a few 100 million years, the galaxy itself will be dotted with warm lights of human habitation. That's not fast by our daily measure, but it's nothing on cosmic time, less than 1% of the sun's lifetime, and only an eye blink in galactic history. In the end, what matters is not how fast we go, but that we keep going. In many ways, ambition, rather than resources, becomes our limiting factor. Deep space habitats are not just stepping stones to other stars, they are the first proof that humanity can live without them. Each one is a seat of civilization, capable of surviving anywhere that energy and matter can be found. Long after Earth has changed beyond recognition, those little worlds will still be turning in the dark, carrying life, memory, and purpose onward. Between the stars, the light of our species will continue to burn, not as a single beacon, but as a constellation of homes spread across eternity.